Supplemental math videos from Circle Christian School. Exponents the SAT way. Really? This is some sort of exponent example? I know that's what you're asking yourself. A lot of what happens with the SAT is actually a math thing called deconstruction. Many of the problems require figuring out how you got there before you can even begin. Here's why you need to know a little bit more about the math rule than basic SAT strategy. One of the examples that I like best from this lesson in the book here is the one that goes, if 3 to the power of k plus 1 minus 3k equals m, then what is 3k plus 2 in the terms of n? Now, as you look at this, there's a couple of things that you need to be able to see. For instance, realizing that there's powers going on says, hey, I got to think power rule. And a lot of the questions are phrased in if this, then that. And the other keyword here is terms of. Looking at the ABCD will let you usually see that what you have to do is find out in terms of how would it be written, what would it end up being if m is the x. You know, what's the variable? In terms of says, what's the variable? All right, here's a little bit of that deconstruction thing. Since I saw powers to begin with and the value that I need to get for m here has something to do with the powers, the k plus the 2, then I realize I'm going to have to work with some same bases. So going back, deconstructing, I just go back to power rule number 1, which says same base times same base, add the powers. So if we look at 3k plus 1 in a little bit of a deconstructed way as 3 to the first power times 3k, then we can break the problem up into having all same bases all together. And each one has a power. Now, where it gets a little wacky is that minus the 3k, because we're not able to use any of the power rules because power rules are all about multiplication, not addition and subtraction. So taking a look at it here, and unfortunately there's a little bit of a left out step in the example of the book, so I hope this will fill in. What we need to do is factor out a 3k. Both of these problems have 3 to the power of k, same base, same power. You can always factor out same base and same power. So that gives us 3k. That's what I factored out. And if I factor out a 3k from the first part there, 3 times 3k, then I'm left with just a 3. The k's gone. And if I take a k out of the second part there, out of the 3k, that just leaves us 1, because 3k divided by 3k is 1. And that still equals m. All these are equivalent, they're just deconstructed. Okay, so 3k times 3 minus 1 gives us basically 3 minus 1 is 2. That's where the 2 comes from. So we have 3k on the outside times 2 equals the m. Well, we need to get that 3k by itself. And so I'm going to divide a 2 out of both sides, and 3k then equals m over 2. All right, we did what we did so that we could actually finally answer the question. Now we're going to do some substitution. Realizing that what we started with, or where we wanted to go, was what's the value of 3 to the power of k plus 2, has that same power rule going on it. A lot of times, whatever you did to the front part of the problem in the if, you're going to also do in the second part, the therefore part. So I'm going to deconstruct the k plus the 2 here. Same thing, same base, different powers. We just add them together. And I've deconstructed because we found out that 3 to the power of k equals the m over 2. So that's what we're going to do. We're going to sub it back in to something that we found, and that will allow us to now find the value in terms of m. That means the variable inside the term here is going to have an m in it, no k's, and we just do the math. Gives us a 9. Remember, that's a 9 over 1, so the 9 times the m's on top, and the 1 times the 2 is the 2 on the bottom. Woo! All right, here's the deal. I don't want you to get discouraged, because you're going to look at this and go, how will I ever be able to do this? SAT has a language. It has a thought process all of its own. The more you see it, the more you do it, the more you investigate it, you start to figure out how they're thinking. And it helps us in being able to think into an answer. A lot of times it's going to be getting partway there, eliminating, see if we get real close. And then you're going to see how they do it, what the tip is. So the tip here is sometimes we have to go back to powers. A little bit about radicals. When you multiply radicals, the square root of a number times the square root of another number, the numbers are just multiplied together. So square root of 3 times square root of 7 equals the square root of 21. All radicals are best when they're simplified. I use the rule of breaking it down into my prime factorization trees. There's a couple of ways you can simplify a radical. So I'm breaking it down. As I break it down, I find 2 factors. If it's not a prime number, I don't circle it, and I got to keep breaking it out, making those branches. So 6 is 2 times 3, and 4 is 2 times 2. All of those are a prime number, and when I get to a prime number, I circle it. That's my little root ball. So it takes 2 for 1 to escape. When it's a square root, it takes 3 of the same base for 1 to escape. If it's a cube root, etc., etc. So you'll see that we have here 2 2's, and he's going to go on the outside. Twins end up on the outside, and anything else is a factor and is on the inside of the radical. So the 6 is 2 times the 3. Another way to do it is you could break the primes. If you're just really good with multiplication, you got a 6 here and you got a 4 here. You can go ahead and do a little bit of work. There's a 2, and the 6 is left over. Some of these you just have to get used to seeing. Now, the deal is you're not going to be able to really use a calculator for a lot of the radicals because the better answer is always a simplified radical. So you have to be able to see it both ways. So the way that you would do this is you would put 2 square root 6 into your calculator and see if it gives you the same run-on decimal number, and that way you can match them up. When you add and subtract radicals, you need to have like radicands. That means you can only add a square root 7 to a square root 7. The number in front is just a coefficient. It tells you how many square root 7s you have. So it's just 2 minus the 5, which gives us a negative 3 square root 7. All radicals have to be rationalized. That is, you cannot have a radical down in the denominator. And the reason why is that that number is not an even number of pieces of a pizza to be down there. A denominator is how many pieces have you cut your pizza into, and it has to be a whole number. So to rationalize, you'll remember that anytime we have a square root and we multiply it to itself, it comes out of the radical. So that's what we're going to do when we rationalize. I have a square root 3 down below here. So I'm going to multiply it by itself and that's going to give me a nice denominator here. In fractions, whatever you multiply to the denominator, you have to multiply to the numerator, and we get 12 square root 3. Radicals always have to be in simplest form. With radicals, you're going to simplify, 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 and when you think you're done, you're going to have to simplify some more. Number to number, letter to letter, radical to radical. And we end up with 4 square root 3 because the 3 goes into the 12 4 times. Number to number. All right, cube roots, same game. The difference is instead of a radical multiplied to itself, because we have a cube root, we have to do it 3 times before the number could come out. So the cube root is 7 times cube root of 7 times the cube root of 7 equals 7. And whatever we do down below, we have to do up top. I just expedited matters. Instead of having all those little cube roots of 7, I just did the 7 multiplied to the 7 gives me a cube root 49. And we have to check to see if it's been simplified. And so I'm going to take 490 here. I'm going to make that prime factorization tree. I'm going to break it up into what we had there. And that gives me a 7 and a 7. There's my little root balls. 10 is 2 and a 5. Notice that there is not 3 of them. It takes 3 for one to come out on the outside. So yes, it's simplified as much as it can be.